Hi, good morning. Today I'm going to talk persistent caching based on NVMe. So I'm Jeff, so I'm the co-founder and chief architect of EloqData. So previously, I was a principal researcher with Microsoft Research. And more personally, I did my graduate study at UC San Diego. So for the DRAM-based caching has always been a cornerstone of supporting real-time, low-latency apps. But from time to time, users still may face issues. For example, DRAM capacity is still limited compared with fast-growing data volumes. And most recently, there has been news about possible supply chain disruption about the DRAM. So besides DRAM, actually, there are other opportunities for real-time, low-latency apps, and one is NVMe. So NVMe is a stable storage media that has made a lot of progress in the last couple of years. So today, a single NVMe device can deliver amazing performance. So here is one product you can purchase from the market right now. A single device can deliver over 3 million random LPS. And this is just one device. Actually, a single server can have 6 to 8 devices. So if we add all these numbers up, a single server can deliver over 10 million random LPS, which is astonishing, actually. Well, even though NVMe has great numbers, but it's not free lunch. So here I reference one academia research showing that if we deploy existing storage engines or storage systems on top of NVMe, we cannot get peak performance. And the gap actually is quite large. So the main explanation behind this is that while the conventional engineering practices, such as multi-threading and synchronous I/O, are not sufficient. So we need new tools to unlock the potential of NVMe. And they are coroutines and asynchronous I/O. So the very essence about the NVMe is that it calls for massive amounts of parallelism. So conventionally, we rely on threads to do this. So each time a thread sends an L request, the operating system, we need to put that thread into sleep, causing context switching. And later, we need to wake it up. And also for each time there is a synchronous I/O, there's a syscall crossing the boundary between the user space and the kernel space. Again, there is some overhead. So conventionally, we never talk about the costs of context switching and syscalls because they are negligible, basically. But right now, we're talking about millions of LPS, or even tens of millions of LPS. On this order of magnitude, we need to care. So the coroutine is a lightweight. You can think it's a lightweight thread, and context switching for a coroutine is much, much faster. But our measurement only takes less than 10 nanoseconds. So it's very fast. And also with asynchronous I/O, it's possible to dramatically reduce the number of syscalls. And finally, I think with coroutines, there is a unique opportunity to tackle tail latency. The reason is that conventionally in the threading model, every thread runs as fast as possible. There is simply no coordination on the resource consumption across threads. And the operating system, which is responsible for scheduling, has zero knowledge of what threads do. For the coroutines, everything is done at the user space. So developers, we know what each coroutine does. So we perform their scheduling in our space. So there is a very unique opportunity. But when we move from the programming from the threading model to the coroutine model, I think the very important aspect, in my view, is that we need to keep in mind is that coroutines are really susceptible to blocking. So of course, I/O is a major source of blocking, but right now we have asynchronous I/O, so that part is solved. But there are other sources of blocking. So here is one example. So in the coroutine, I may invoke a function. And inside the function, there is a thread synchronization. Well, the thing is that this synchronization may cause the physical thread to be blocked. Well, in the coroutine execution, usually a single physical thread is associated with many coroutines. So blocking this physical thread means that we will block all the coroutines associated with this thread, so which is bad. OK, so we have the new hardware, we have some new tools, and we have some guidelines. So what we can do about it? So this is a project we've been building at EloqData, which is called ElloKV, which is a Valkey-compatible key-value database. It's a persistent database based on NVMe. So the architecture-wise, most modules sound familiar. You can find similar modules from the Valkey systems or other databases. So on the top, there's a networking layer. In the middle, there's a memory layer, in-memory access, in-memory data structures. We have a transaction module because we target persistence. But this module is optional. You can turn it on to log in Valkey commands or can turn it off. So underneath, there is a storage engine based on NVMe. So the exit path is very similar, but there is a background task, a long-running background task known as checkpointing. So that process periodically scans the memory for modified data items, and we flush those data items to a stable storage engine. And this process is asynchronous in the background, so at the same time, we can upload those changes to the cloud. I think what's interesting in this, I think in our system is the really execution model. So basically, everything is a coroutine. So from the networking layer, when a network message arrives, we create a new coroutine to parse the message, and we start accessing the in-memory data structures. And in case there is a data conflict in this process, we simply context switch this coroutine to a second query. And if the second query needs to access storage engine, again, causing an I/O, we're going to context switch the second coroutine again. So yeah, here is the summary. So basically, everything is a coroutine. So as for coroutine scheduling, I think it's very important is that the coroutines need to yield or schedule proactively. So we need to do that proactively. So it means that each time each time the coroutine sends out a request, or it encounters a data conflict, or if this coroutine has run very long, we want to switch that. So the last point is very important for the tail latency because we don't want some tasks, especially background tasks, to occupy the CPU too long to impact the tail latency. I think that's very important. So as for the scheduling of the coroutines, the very important difference from the threads is that we actually need to inject those yield points in our code by ourselves. So actually, we need to evaluate at which point we want to insert those yield code in our code. So we need to evaluate. So we developed like 2 guidelines in our engineering practices. The first one is that, of course, we can measure the execution time. If that has been too long, we want to switch. So this is one example in our storage engine. The pattern is that the storage engine receives a pool of requests. And there is a loop to process those requests. And of course, we can monitor the time. The second pattern is that in you can actually evaluate how much memory your code has accessed. If the memory exceeds a certain threshold, you also want to switch. So the second example comes from, again, a background task in our system, which needs to do a memory copy. That chunk of memory is greater than 1 megabytes. So the interesting part is that if you look at the average latency of this copying 1 megabytes of memory, actually it's very fast. It probably dozens of microseconds. But if you observe the tail latency, it could be as long as over 1 millisecond, which is too long for tail latency. So in that case, we just split that one large copying into many small copies. So from the example, you can see that there can be some mentality change. It's not only about how we want to run the code as fast as possible, but also care about the fairness. So the second lesson I want to talk about is about CPU usage. Today, if you look at the NVMe discussions on the internet or the manufacturer specifications, they have amazing numbers. But I think one factor often missing from those conversations is the CPU usage, and which is how many CPU resources it's going to cost to achieve those numbers. For example, today, if you look at the NVMe devices, usually the spec says the random read throughput is very high, almost as close to the sequential reads. But actually, it's going to cost much, much more CPU resource to achieve, for the random reads to achieve that number. And similarly, for the random writes, are going to cost much more CPU usage than the random reads. So I think this kind of factor, we need to take that into consideration when we design our storage engines or systems, because it depends on it determines how do you want to decide what data structures you want to use and what algorithms you want to use. And for this third lesson, it's about, well, for low latency systems, we want to tackle the tail latency. Of course, the first one is that I mentioned this before. As coroutines, you want to switch coroutines proactively. You don't want monopoly of the CPU usage. The second one is that as for the storage systems, you want to make sure the storage system also incurs a fixed or a predictable number of I/O counts. So that's why in our storage engine, we actually adopt the B+ tree, because the height can't be fixed. And also, but in contrast to the conventional databases, where there is a single giant B plus tree, actually we perform data partitioning even for a single node system. And also that's important because you want to control the height of the tree. You don't want to say the height grows larger as the data volumes grows. So that's also important. So we have the technique, we have the new hardware, we have some techniques, then what kind of performance you can get out of the NVMe today. So here I just want to give you an idea, so what you can expect, especially relatively compared to the in-memory access. So probably will give you some guideline. So here in the first testing, we just changed the data volume from 20 gig to 2 terabytes. So 20 gig, of course, that data can fit into memory, so everything is in-memory access. So the workload is read and completely random. So completely random means that if the data set is 2 terabytes, every query has to hit the disk. So here is that you can see basically the throughput or the QPS, the peak throughput, the QPS, is probably like 600,000. But for the NVMe, if everything hit disk, the QPS is half. So basically that's giving an idea what you can get out of this NVMe, today's device or software systems. For the tail latency, of course, it's going to be longer, but I think it's still manageable. In the second testing, actually, we changed the workload. So now we have reads, we have write, it's hybrid, and also we also limit the throughput. So just in case your application don't need to push the limit of the in-memory performance, so actually we can further improve the tail latency. It's around 3 milliseconds. On 2 terabytes of data, it's completely random access. So, to conclude my talk, so basically, conventionally, DRAM-based caching seems the only option for long, real-time, low-latency apps. But right now, NVMe-based solution could be a viable solution for some applications. For example, the data volume grows very fast, and it's very hard to predict the locality. And if the applications are very cost-sensitive, then you can consider using the NVMe. So it really needs some cost for some new engineering tools to unlock the full potential of NVMe. So in this case, the coroutines and asynchronous I/O. And also, I think the coroutines has unique opportunity. We can do this user space scheduling to tackle tail latency, but this definitely needs some careful considerations and designs. So yeah, I think that's the end of my talk. Yeah. Oh, by the way, also, yeah, this project was open sourced, so if you are interested, you can take a look.